clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. My brothers, they are all underground. We shovel and fill till we come to the crown. From the river to the sea, St. Johnston, wait for me. I'll walk my boots clean someday. I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. I laid the ground for the new Jubilee. The Mersey and Thames owe their soundness to me. From the river to the sea, but Alec will wait for me. I'll walk my boots clean someday. I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. I've blasted for rails and canals, cheek with the pit boss and crack with me pals. From the river to the sea, Van Cranna, wait for me. I'll walk my boots clean someday. Our girls of the great TBM, Strata or Sleech, they mean nothing to them. From the river to the sea, sweet Rhonda, wait for me. I'll walk my boots clean someday. I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. I've witnessed the fall of the face, when you labour in fear for the lives of your mates. From the river to the sea, oh trim and wait for me. I'll walk my boots clean someday. I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. Done. I'll lie with my lass and I'll stand in the sun. From the river to the sea, get in, you wait for me. I'll walk my boots clean someday. For I crew with a pick of the crowd. We are strong, we are bold, we are one, we are proud. And from Brno to Bray to the wild Atlantic way, we'll walk our boots clean someday. I'll walk my boots clean someday. Sure as a bull in a valley of clay. I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. My brothers, they are all underground. We shovel and fill till we come to the crown. From the river to the sea, St. Johnston, wait for me. I'll walk my boots clean someday. I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. I laid the ground for the new Jubilee. The Mersey and Thames owe their soundness to me. From the river to the sea, but Alec will wait for me. I'll walk my boots my boots clean someday. I've blasted for rails and canals, cheek with the pit boss and crack with me pals. From the river to the sea, one crown wait for me. I'll walk my boots clean someday. Our girls of the great TBM, Strata or Sleech, they mean nothing to them. From the river to the sea, sweet rendezvous for me. I'll walk my boots clean someday. I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. I've witnessed the fall of the face when you labour in fear for the lives of your mates. From the river to the sea, oh trim and wait for me. I'll walk my boots clean someday. I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. Soon this shift will be done. I'll lie with my lass and I'll stand in the sun. From the river to the sea, get in, you wait for me. I'll walk my boots clean someday. For I crew with a pick of the crowd. We are strong, we are bold, we are wild, we are proud. And from Brno to Bray to the wild Atlantic way, we'll walk our boots clean someday. I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday. Sure as a bull in a valley of clay, I'll walk my boots clean someday.
Good evening all, and welcome to tonight's British Tunnelling Society evening meeting. Tonight's lecture is on Hinkley Point C nuclear power station, tunnelling and marine project, and our speaker this evening is Matt Fowler. Matt is a site agent working for Balfour Beatty on the HPC Marine Works project. He has worked on the project for almost 4 years, with much of his time focused on the tunnel heads construction. Since the completion of his studies at Cardiff University, Matt has spent his career working on large-scale infrastructure projects such as the Filton Bank 4 track railway scheme and the Hitachi Intercity Express rail depot. He's now looking forward to the future offshore campaigns at HPC Marine Works, which will bring with it many new and exciting challenges. Welcome, Matt, this evening.
Okay, thanks, Kate. Good evening, everyone. Thanks for the introduction. So first off, I just need to make some apologies. The plan this evening was to take you through the full scope of works up to where we are now on site. Unfortunately, one of my colleagues is unable to join us this evening due to some last-minute unforeseen circumstances. What this means is that the presentation you're going to get is only really half of the picture. And importantly for you guys as members of BTS, it's the tunnels bit that we're going to be missing tonight. Don't worry though, there's every intention to run through this in another session in the near future where we'll pick all of that up. So what that also means is that my range of knowledge is very much limited to the heads construction. So please bear with me for anything outside of that when we get to question time at the end. Anything that we can't answer tonight, we'll pick up and answer offline. And of course, you can raise questions through BTS and they'll get in touch to communicate those back to you. So without further ado then, let's get into it. Okay, so I'm sure you've all heard about Hinkley Point C, based down in Somerset. Some of you may even have a pretty good insight into what it is, what I'm going to cover today, if you managed to catch the BBC documentary, which has been on for the past couple of weeks. HPC is obviously a project of magnificent scale and complexity, being the first nuclear new build in a generation for the UK. It's tasked with answering a significant portion of the UK's demand for low carbon energy future. And as part of this Balfour Beatty, we have the pleasure of delivering the key infrastructure for the absolutely critical cooling water system. And what this broadly entails is the construction of 3 tunnels under the seabed of the Bristol Channel, the placement of some intake and outfall heads onto the seabed, and then the subsequent offshore connection works to allow the cooling water to reach the tunnels. More specifically then, of the 3 tunnels, 2 are the intakes for the cooling water, and they cover a distance of about 3.5 kilometers each. The other is the tunnel for the water outlet, which is about 1.8 kilometers in length. So the topics on the screen there were the intentions for today, but again, unfortunately, I'm just going to take you through our operations shown in bold, both of which take place away from the main site at HPC, just on the outskirts of Bristol in Avonmouth. Okay, so the plan, as I mentioned, was to show you where the segments end up. We're going to skip through that, and I'm going to be jumping straight into our off-site fabrication facility, where the segments and the heads were put together. On the screen there is a snap of our main storage yard, which was a key logistics hub for us controlling quality check-in and certification before the final distribution of the segments to the tunnels team down in Bridgewater. Okay, so for starters, all of the segments are traditionally reinforced rather than fibre reinforced. Then for the intake tunnels, as you can see towards the top side of the screen there, they are 6 meters in diameter. The design comprises of 6 segment types that make up that ring, S1 to S6. So to facilitate the 2 intake tunnels, the intake segment production figures were in the region of 28,000 segments, totaling almost 4,700 individual rings. Similarly, the outfall tunnels are 7 meters in diameter, and they're comprised of 8 segment types, S1 to S8, and with only 1 outfall tunnel and it being of a shorter length, the outfall segment production figures were in the region of 10,000 segments, totaling around 1,200 individual rings. So although there's an overlap in the naming conventions of the segments with S1 to S6, the items are unique to their tunnel, as you'd probably guess based on the diameter variation. So moving on then, here's an overview of our production facility in Avonmouth. In the main image on the screen there, you can see the factory itself. You can see the external gantry crane, the segment for storage facility, not the main one I mentioned earlier on, but a smaller one we've got right next to the factory. And then loading bay for the wagons just along the side there. So towards the bottom left of the image, you can also see the trial ring assembly area, which is where the physical trials were performed during the early stages of manufacture to verify that the segments were going to be suitable for use in the tunnels. After many successful trials, we then switched this to a virtual ring every 500 rings. And this was done by 3D scanning the completed segments and reconstructing them digitally into a ring. So by removing the physical works, we de-risked the operation and gained a big tick in the box against our commitments to CDM. So in other words, we designed out the risk of having to perform that physical trial ring. Also in the very bottom left of the image, you can see a building just on the corner there, and that's our UCAS accredited lab, which allowed us to undertake all of the testing requirements in-house. Okay, so the internals of the segment factory then, they were fully designed and supplied by CBE in France, and the solution developed for us was a moving floor carousel system. With this, we were able to facilitate the production of all of the segment types for both the intake and the outfall rings. And in total, the carousel held 66 molds, so that being 7 intake ring sets and 3 outfall ring sets. Carousel system was digitized by our BIM team, and the visualizations shown on the screen there are an extract from a 4D model which they prepared. So this sequenced video takes the viewer on the segment journey from start to finish along the carousel system. So importantly, this wasn't just a shiny display of our digital capability, but there were some tangible benefits to it that we were able to get from the visualizations, as we could tailor them to the ever-changing needs of the project. So, for instance, when COVID struck, all of the modelling was updated to show 2-metre exclusion zones around personnel, highlighting where there may have been interfaces and any requirements for additional control measures. Similarly, the videos we used during inductions and briefings, and they had the added benefit of us being able to overlay text in multiple languages that meant we could confidently ensure the multilingual workforce were engaged and understanding of the works. Okay, so the team, although we've got an advanced production facility with many layers of automation, we really mustn't forget the people involved in the operation, which are absolutely critical to the smooth running operations. On the screen there is just a portion of the people involved on a daily basis. Of course, I mentioned pre-COVID, that photo. So operational shift patterns have fluctuated throughout the life of the project, but ultimately we found the sweet spot with operating on a schedule of 24 hours a day, Monday to Friday, with a 12-hour shift on a Saturday. And what that allowed us was 1.5 days of downtime for preventative maintenance, which ultimately led to greater production outputs by mitigating downtime during the working week. So what this meant in terms of labour was back-to-back shifts with a team of approximately 75 per shift, spread all across the various functions for production, lifting, logistics, quality, and others. Okay, so I'll take you through some pictures from the factory operations. So starting on the top right there, we've got an image of our on-site batching plant, which provides a dedicated concrete supply for the segment factory. This is located no more than about 20 meters outside the factory, and then the image you see on the bottom right of the screen is known as the bullet. So this travels on rails directly back and forth between the batcher and the depositing point above the molds within the factory, which you can also see in the top left image there. On the bottom left is a snap of the molds being prepared for concrete with their gaskets and their reinforcement cages installed. And this is also where cover checks and final QA operations took place prior to the concrete actually being placed. Down the center of the screen is a view of the internal gantry crane in operation there, moving segments between the various workstations. Okay, so to summarize some of the facts for you then, intake segment production figures were around 4,660 rings, or almost 28,000 segments. Outfall segment production around the 1,200 ring mark with almost 10,000 segments. The best cycle time that we recorded for the preparation and build of a single segment was 8.5 minutes. Production time for a full intake ring or 6 segments, typically 54 minutes. The time taken to achieve a strength of 30 megapascals while traveling through the curing chamber was 7.5 hours. And the total quantity of use for all of the segments was in the region of 77,000 meters cubed. So, and just a few more which aren't on the screen there. So in 2020, we performed around 130,000 safe lifts across all of the segment production operations. And perhaps most notably, we completed more Class 1 nuclear grade concrete pours than the rest of HPC combined. Okay, so having taken you through the segment operations there, I'm now going to run through some of the most critical components of the cooling water system, which are the intake and the outfall heads. These are large reinforced concrete structures which are being manufactured off-site, right next door to the segment factory, which you can actually see in the left of the image there. And these are destined for placement on the seabed of the Bristol Channel, ready for their final connection to the tunnels. So this is an overview of our site layout, which is based in the Port of Avonmouth. As I mentioned earlier on, there are 3 tunnels in total, and to facilitate the tunnels with the cooling water they need, each tunnel has 2 heads, giving a total of 4 intake heads and 2 outfall heads. The site layout was developed based on the need to move these structures offshore for their final final life. So they're set ready for an easy transition to load out onto a barge in the future, with the key edge just out of shot on the right-hand side of the screen. So firstly, then I'll go through the outfall head structures, which you can see pictured there. So there are two of these nuclear classified structures, and each has a footprint of about 16 meters by 16 meters, with an elevation of around 8 meters. Each one of these has around 245 tons of reinforcement embedded within 1,100 cubic meters of concrete, and it also has significant amounts of embedded high-grade stainless steel items, which needed to be managed throughout the build. The structures were split into 11 distinct pours, and once complete, the finished product weighed in around 2,700 tons, which is of critical importance for being able to undertake the offshore placement in the future. And then the larger of the structures, which is the intakes. So these are also nuclear classified, and these stand at almost 45 meters long. They're about 17 meters wide, and again around 8 meters high. Each one of these contains 1,500 meters cubes of concrete, specially designed nuclear qualified concrete mix, which was needed to combat not only the reinforcement density, but also the next almost 100 years that they're going to spend amongst the marine life. And the outfalls use that mix also. So with a nuclear qualified mix, that means extensive mix design approvals and really no making it up on the day. So the intakes were broken down into 9 main pours based on their shape, the complexity, in-cast item embedments, and various other influencing factors. And once fully formed, these structures would weigh in at around 4,500 tons each, which is again of critical importance. So due to the weight restrictions for that final placement offshore, monitoring of the weight throughout has played a key part, and it's influenced some of the design and construction decisions, such as the selection of lightweight permanent formwork. I'll also note at this point that we actually have to weigh these structures on 2 occasions throughout the build to verify that we've got that final weight before we move these things offshore. Okay, so it's easy to look at these structures and just consider them as large concrete blocks, but the shape, the size, and the complexity of them makes them some of the most densely reinforced, geometrically complex structures in the country. Because of this, it was absolutely critical that the reinforcement was detailed to be class-free. Otherwise, the stoppages during construction could have just been exponential. To combat this, we engaged a 3D reinforcement detailer called ADA, who were able to develop the designer's intent into a fully clash-free model for site implementation. This found that the original 2D detailing that you typically use had tens of thousands of clashes, which were all able to be resolved before placing the first piece of steel on site. Throughout the construction, we then had this 3D model available as a tool for both of the types of heads. We had engineers and supervisors equipped with tablets who could then delve right into the detail while stood in front of the fixers to make sure that everything was correct. And when you consider that in many cases the positional tolerance on this reinforcement was plus or minus 5 millimeters, this was absolutely critical to the success of the build. And then as a final note on the reinforcement, it's really hard to get a picture of what you see on screen there, but each intake head has approximately 120,000 individual bars. More than half of these were shear links, which equates to really low tonnage outputs when you start to consider productivity. And the software was able to break down the reinforcement by shape, tell us what that was going to look like when we came to the build, and then we could then feed that into the schedule and exercises. So I also mentioned the in-cast items, and what I've shown here is a screenshot of just 1/2 of an intake head, which clearly shows you the significant sum of critical embedments which we needed to manage. So some of the key components included the 8 super duplex lifting lugs, which weigh in at 5 ton per piece, and these are critical in undertaking the offshore placement operation. Some of the others, we've got 48 number copper nickel baffle plates. So they weigh in at around 1 ton each also, and they're for controlling the water flow into the shaft of the structure. And then we've got 186 copper nickel bars, and they're for stopping large debris making its way into the tunnels. So there's many other items, some of which are pictured on the screen. But it's probably worth noting some of the roof components, which you can see just towards the top of the screen there. They include a locking mechanism for the cover slabs, which is basically a plug that goes in the top of the head. And there's also hatches for future diver access if ever required for maintenance. So in total on the intake heads, there's around 128 tons of incast items. That's split between permanent and temporary works items. Okay, so some images of the early stages of the construction. At this point, we needed to fix in excess of 200 tons of the reinforcement, so more than 25% of the total tonnage, just to achieve the first concrete pour. And that first pour was only 500 mil in height. So what this meant was that all of the focus was on the critical tolerances for the reinforcement fixing. We had to ensure that every single starter bar was cast into the correct location. We couldn't have anything off angle, otherwise the knock-on effect would be exponential. So check-in was required for every single piece of reinforcement and consisted of a full suite of checks by 4 different parties. So we had 2 in-house, 1 supplied by a subcontractor and 1 by our client. Here we are then ready for the casting of the second pour. So after we achieved that first 500 mil pour with 25% of the reinforcement fix, the second pour would be one of our biggest challenges, as it was the largest at 600 meters cubed per head. At this point, we had fixed almost 400 tons of the reinforcement, so more than 50% of the total, just to achieve the second pour out of the 9. And after casting this, we would only be around 2.5 meters tall out of the required 8. One of the biggest challenges for this pour was the thermal management of the concrete post-casting. So due to the deep, thick sections, we were going to generate lots of heat, and this posed a really high potential for exceeding temperature specifications. So to manage this, we used chilled water from the batching plant. We also started the pours during the middle of the night. There were other control measures in place, such as the installation of the formwork, covering of the top of the pour with thermal blankets once completed. And then we had monitoring embedded within the pour so that we could keep a track of it for the next several weeks until we were happy that the thermal management had tailed off and everything was satisfactory. So topping out. So as we approached the top of the structures, the decision was taken to revisit the design. And what we did was optimize some of the reinforcement to ensure that the design was buildable without compromising the concrete integrity, because some of the areas of reinforcement density were as high as 900 kilograms per meters cubed, and this caused major concerns for concrete flow. So you can see on the right there, the final pour on the roof slab of the structure, marking the completion of the main structures. On the left there, you've got it just at the top of the foundation chamber, so about 3 meters off the ground, with still the screen chamber and lower chamber to be built. Okay, and then just an overview from start to finish, really. On the left, you've got the 2 heads. You can see second from left and fourth from left. Those 2 are just starting production, and the others are yet to start. On the right, you can see all heads completed, with the final pour of the final head ongoing in the picture as you see it. So these pictures were captured about 2 years apart. And then a few more pictures just of the finished products there. So I think looking pretty identical to the 3D visualizations that I showed you earlier on. Obviously the intake there on the left, and the 2 outfalls on the right, and that key edge I mentioned ready for subsequent loadout in the future, ready for going offshore. Okay, so the numbers, they're really one thing, but what I wanted to try and do was give you some perspective to the size of these structures. On the left there, you can see our works manager modeling alongside one of the outfall cover slabs. And on the right, you can see the scale of that cover slab within the head itself. And then when you consider that the intake heads are more than twice the size of the outfall heads, you can kind of get a picture that the scale of these is really something. And I'll just touch briefly on the cover slabs because I haven't really mentioned them throughout this, but essentially these are lids to cap off the structures, as I did say, but these are left out of place to allow all of the offshore tunnel connection works to happen. And they're really one of the last pieces of the puzzle to be fitted once the tunnels are fully operational. Okay, so from me then, across the two packages of off-site fabrication, there are a lot of similarities in the lessons learned. Firstly, collaboration at an early design stage to incorporate buildability was absolutely key to the success of the reinforcement fixing and to the concrete placement. They really do go hand in hand. So the top image there shows the array of couplers which were added to coordinate with the pour splits that we agreed. This aided in personnel safety and also gave us clear access paths through the reinforcement to be able to complete our pours. The nuclear specification requirements being another one then. So especially in relation to concrete finish, nuclear specification absolutely not to be underestimated. There was significant time and resource allocated to minor finishing and repair works, which would normally, be acceptable on a normal project, but in nuclear environment where we're looking for the integrity of the structures to, no doubts about it. It really is something that needs to be considered. The requirement for smooth communication across the various operational functions, a pretty obvious lessons learned on any project, I think, but due to the complexity, this was just ever more present. So getting that communication across the operational functions like delivery, quality, lifting, the client included, it really had the capacity to make or break the project. And an easy example of this is that 4-tiered check-in process, which I mentioned. If that didn't have a lot of collaboration across it, then that really could be a process which crumbled. So development of project-specific processes and briefings. Again, another one that you could say about any project, but it really does feed into the complexity here. So, for example, in the factory, that preventative maintenance regime, that was really key to the production success. And on the heads, the clear expectations and expanding the reinforcement specification, briefing it to the guys doing the work, but also those check-in. These little things that all contribute to removing ambiguity and making expectations clear, they really are key in delivering success. And then finally, and most importantly, with such a complex job, remembering to look back at what you've learned and implement all of the changes progressively, doing this on a regular basis, whether it's based on key milestones or on a monthly or weekly period. But through thorough lessons learned and root cause analysis, the segment production was able to escalate a right first time rate to above 95%, which is just incredible, really, considering the specifications for the nuclear environment, which I mentioned already. Okay, so I think we're now going to switch to a video, which you should hopefully see playing on your screens very shortly.
In front of these doors, and we've got the seabed.
Okay, thanks everyone. So hopefully that gave you a bit of a flavour of what we were up to in 2020. Again, apologies that we didn't get to see the tunnels today, but hopefully you caught some images during the video. And I think we're now going to open the floor for questions. So.
Thank you, Matt. Yes, appreciate not quite the full offering that you would hope to share with us tonight, but we're looking forward to welcoming you back to, well, firstly, also hear more about the works you've been directly involved with, but also for your colleagues as well. So there are a couple of questions in. So what I could ask is everyone that's watching on YouTube, if you've got some questions, if you could put them in the chat section, that would be great. The first question we've got in is from Roger Bridge. Are you able to comment regarding the percentage rejection rates for the segment production process?
Yeah, I'll do my best to answer that one, Roger. So as I mentioned, we managed to get the right first time rate up above 95%. It's fair to say it didn't start out at that position. I think mainly to do with getting to grips with that nuclear specification, understanding how the concrete mix behaved, understanding the best method around check-in and the undertaking of repairs in a smooth, streamlined manner that fits the carousel system that the segments were being spun through. But yeah, ultimately we did manage to get that to a really good rate.
Okay. The next one then is in from Divik. Quite a monumental task. Absolutely agree. Looks like quite of a maze when you look at those images. What was the extent of QA checks required while typing the rebars and pouring the concrete? Does that say tying the rebars?
Yeah, I would guess that's tying.
Yeah.
So it's a massive subject to try and cover in a quick response, but one thing I didn't mention was, so the reinforcement, for starters, every single piece of reinforcement, every single individual bar that came through the door was checked before it was fitted. That is like nothing done anywhere else in the country. That was our first piece of QA. That allowed us to make sure that the product going onto the shop floor, so to speak, was right before it even got there. Once it got there, we had 4 independent checks for every piece of reinforcement that was laid. So that would be, a couple of engineers, the client side, and our quality team, making sure that everything was there and it was right. In terms of the actual checking process, for the pour 2 that I showed alone, so that 600 meter cube pour, we could end up with 1,000 check sheets for that one pour on one head, and that would cover your concrete placement, all your pre-pour inspections, all of your reinforcement checking that your ties were done to British standards, the checking of in-cast items if there were any embedments, and many other things.
And I think a linked question again from Divik. Was there any differences in the extent of check-in for the heads versus the segments?
I think the main difference really is the scale. In terms of the actual specifications, very similar specifications. For instance, concrete finish, virtually identical. It's really just about that scale. So you do a pour on a concrete, pour on a head. You could be looking at a surface area of 100 meters squared. You do a single segment, you're talking at a small surface area that you need to go through, but the checking process was the same. When I talk about concrete finish, we could be talking about blowholes in the concrete finish, which are 10 mil big. Every single one of them checked for depth, repaired to make sure that it wasn't going to compromise the integrity of the structure.
Okay. We've got another question in from Daniel Pittle. Thanks for a great presentation. He's got 2 questions. Number 1, how come the intake head structures had a much higher rebar density than the outfall ones? And number 2, was the CO2 due to materials production considered?
Okay, so question 1, I think maybe I gave a skewed impression there, but really the density across the 2 structures was really very similar. The intake density was probably more larger diameter bars that were going to be difficult to displace and would cause you more issues if you came across any clashes or changes in the reinforcement shape because of the natural tolerance of the production for them. In the outfall heads, we've got particularly in the superstructure, there's some more curved surfaces. with a lot more smaller diameter bars, but in tight congested areas, lots of bars flying through. So density is really very similar across the two structures. On the second point there then, so CO2 due to materials. Yeah, I mean, obviously that's a key consideration into our sustainability plan for what we're producing here. I know HPC have got overarching ones for the project as a whole, where they consider the impact of what we're going to be constructing before it even gets the sign off, to start the project. And then as Balfour BT, we've got our own plans in place throughout the build to make sure that we're managing that and, doing what's best for the planet.
Okay. The next one then is in from Tunnel Talk. Why was steel fibre reinforcement not used in the segments? And was steel fibre used in any of the concrete works, e.g. shotcrete, cast concrete linings underground?
In terms of the tunnel piece of that, I definitely, I'll have to pass. Maybe that's one we can pick up and get your response to. And then for the segments, again, I really don't have the answer to that at the moment, but I'm happy to take that offline and get back to you.
I think she's also asking, what about in any of the other temporary works?
Yeah, I'm going to assume that's linked with the tunnels again, so I'm going to have to pass. But as I said at the start, we'll endeavour to try and get you some responses as to how these decisions were made. All right.
No problem at all. So I've got one, because I think we've definitely got time for a couple more in the chat if people want to put them in the YouTube chat. You talked about optimization of the design whilst topping out. Was that something that caused any overall delays, or were the benefits of that optimization, did they bring any time savings? Because it's quite an interesting stage in the process to sort of really be optimizing the design.
Yeah, so there's a few links to making that decision. One of the fundamental ones was that the heads were originally designed to be piled into the seabed. That requirement was removed, which meant that there was the opportunity to review the reinforcement design. When that happened, when we took the decision to review the optimization, we were a little bit lower down the structure. We had the time to go through all the design and process it before the fix was actually going to begin. So, it ultimately, no, there was a cost saving, time saving. Yeah, it was the right decision to make.
So another question from me, what are you working on then at the moment? Because obviously with their estate, obviously you mentioned obviously just then that the solution of the piling has gone away. What are the preparations for when they actually get taken out?
Yeah, so the current works that we're doing here really is getting ready for the offshore campaigns. One of the first operations will be to start dredging in the Bristol Channel. Once we've dredged the pockets where we're going to place the heads, we need to lay a gravel bed down. Once that work is completed, we'll be looking to load out the heads from the dock here, putting them onto barges, getting some really heavy lift vessels offshore, and then we'll be undertaking the lifting operation, placing them onto the seabed, and then rolling on forward to the connection works after that.
Okay. So I think we've got a couple more questions in. So one in from the cost of everything. How did you prevent damage, e.g. corrosion, from sea spray?
Yeah, so I'll do a bit of interpretation there because I think that's quite open, but I'm going to assume you mean with us constructing right on the coast here. So one of the things we actually did was at a very early stage of the project was look into what the impacts of sea spray were going to be, particularly on the reinforcement, which was really prone to corrosion. And from the testing that we did, we actually didn't find any raised kind of corrosion, I guess. We were doing a kind of pH testing on some of the reinforcement, checking for salts and chlorides, and we didn't see any increase, especially after rainfall. It kind of washed off and resumed to normal. So yeah, we didn't actually experience anything outside of what you would normally expect.
Okay. Next question is in from Warren. Can you talk a little bit about how the topside and tunnel works are interfaced together and the timescales to complete?
Yes, certainly. So, okay, so if I pick up from once the heads touch the seabed, one of the next operations to be done is the drilling of the shaft. So it's probably not too clear in some of the images I've shown, but down the center of the head is a around about 7 meter diameter shaft. So what we'll be doing is bringing in some jacket barges offshore, and we'll be drilling through the center of the shaft, approximately 33 meters down to where the tunnels are through the seabed. Once that is done, there'll be a steel liner installed that will be grouted into position. There'll be an isolation cap installed to make sure that we can cap off the water. Obviously, start then breaking through from the tunnel side to make that final tunnel connection. So, I mean, that's extremely high level run through, obviously, but hopefully that gives you a sort of picture of the works that are going to be involved there.
Okay. Next question then is a little bit about what do the nuclear classes mean?
Yeah, okay. So I mean, I'm not going to run you through all of them, but certainly the class 1 nuclear structure that I mentioned, it means it's a critical component to the safe operation of the nuclear power plant. So, yeah, if you look at some of the critical failures around the world, like Fukushima, they've all been because of the cooling water not being able to reach the reactor. So therefore, the cooling water system, class 1 structures.
Okay. This is another one that I'm not sure if you'll be able to help with us. One from Tunnel Talk again. What was the segment production lead time to the launch of the TBMs, either in months or segments in the stockpile?
Yeah, I think I'm going to have to pass on that one again, but we'll certainly try and get an answer.
Okay. Next up then we've got one from Divik. What was the extent of post-concreting check and what checks were carried out post-concreting?
Yeah, so that's a really good question. So once the heads were actually cast, every single surface was inspected again through that same 4-tiered checking process I mentioned. I already touched on the blowholes, so every single blowhole checked. Any cracks over 0.2 millimeters needed to be repaired. So you know, trying to picture 0.2 millimeters is tiny. We little magnifying glasses to go around and inspect these surfaces. Yeah, I mean, the check-in afterwards, no different to the check-in prior. It's absolutely clear that these things need to be spotless before they're ready for install on the nuclear power station.
Okay. We've got another one that you may be able to help us with from Tunnel Talk.
I think I can do this one.
Were the segment reinforcement cages fabricated on or off-site?
Yeah, so the cages were fabricated off-site and all delivered to site and ready-made. Okay. So in the factory, it was just a case of dropping them straight into position and making sure the cover around the mold was correct.
Okay, and then we've got another one from Warren. On such a vast project, is this part of the project well away from the critical path?
It's a difficult one to answer because things change all of the time. But as vast as the project is, the scale of the operations going on at Hinkley mean that everyone is on top of each other. So, for instance, our tunnel guys, I know their entry point down into the tunnels. They need to clear off out of there because someone needs to build a building on the top of their entry point. You know, that gives you a rough kind of impression of the interfaces.
Okay, then we've got one. What was the de-shuttering time kept for such heavy concreting?
So it really depends on which pour, what time of year, how much concrete we were pouring. Effectively, we needed to get to, I think 90% curing before we could stop the curing process. In terms of shuttering, it really falls down to temporary work. So typically around 10 newtons, we could look at striking shuttering, but it just meant if we struck the shutters, we'd have to cure in some other way. So Hessian blankets damped down, or you know, applying a curing agent and things like that. So yeah, it really depends, but there's options there to accelerate the program, remove shuttering if needed, and then kind of push forward.
Okay, then we've got another question from the cost of everything. What will be done with the factory at the end of construction?
So as we are here, we're set up in the port of Avonmouth. The plan is to demob, hand back, so the port can have their space back.
Okay. So I think Another quick one from me. You mentioned obviously the importance of lessons learnt. What would be your number one that you will take to not only the next part of this project that you're on, that you'll take to future projects?
Ooh, that is a very good question. Honestly, I think for me, I'd put it on the slides already. It's really about lessons learned. It's so easy to, to go through a project and not realize what you're learning. We did lessons learned.
The wonderful thing about tunnelling is it actually goes across different sectors. So you can be a tunnelling engineer and work in rail, work in water, work in highways.
Because the space in as cities are growing so fast and the space on the surface is just disappearing and we need to go underground. And so the demand for engineers who know how to construct underground is just increasing. And so that's why the course is particularly relevant at the moment.
The modules cover pretty much everything you need to know about tunnelling in underground space. So from health and safety to design to construction management.
So the course is structured in 1 week blocks. They also enable the course to be taken part-time and they can come and just for the week-long modules. And then they can go back to their work afterwards in between the modules.
You've got people who are coming from industry and able to bring real life experiences and case studies into an academic environment. And that for me is quite unique with this particular course. I haven't seen that in many places.
They are very knowledgeable and learning from them, I can actually relate and learn on how to do better when I bring my work back after this course.
I would say this course focuses more towards what you will experience when you actually graduate and start working.
We get to do a realistic group project at the end of the MSc. That really helps with the transition into the industry.
The design of a tunnelling scheme, but also working out how it's going to be built and even how the contract and how it's going to be managed and organised.
The course attracts students from around the world.
A lot of them have come from work, so they've been working in industry for the past couple of years, coming in with that industry knowledge, whereas I've come straight from university.
Like for me, for example, for a couple of years, I may have forgotten certain things. So it's interesting to learn from someone who has just graduated. I see things in a different way as well.
We've had one young lady who joined us in 2017. She specifically has been involved in quite a number of overseas projects, which I think she's really enjoyed. Again, we did another annual visit to meet the students of the master's course, and we had another postgrad join us, and we were able to offer him sponsorship, and now he works for us permanently.
I'm currently working on the bank station capacity upgrade project, on the final bits of the design of that project.
I think this is a really exciting time to enter into the tunnel and underground construction arena. There's so much work, not just in London, but in the rest of the UK and abroad. And one of the great things about this industry is it will take you absolutely everywhere.
When you graduate from the MSc at Warwick, you will find that everyone in the tunnelling industry is trying to employ you. It is very easy getting a job with an MSc in tunnelling.
I got an offer from ACOM, so I'm starting as a graduate tunnel designer in October, which I think is really good, given that I started the course in October and I got a job in December. And I know from personal experience when I was trying to find a job after the undergrad, it was much more difficult than that. So it definitely opened up new opportunities for me.
Then this evening, just as a brief reminder, we are celebrating our 50 years of service to the tunnelling industry. So that continues to be one of our themes, and I hope you are enjoying the BTS folk songs. Next slide. So this is a bit of a reminder that the MSc Tunnelling and Underground space is still open for applications for entry in October 2021. It's available on a 1 year full-time or 2 to 3 year part-time, with some options to take modules for a smaller award. And there is a bursary of up to £20,000 available through the BTS. and that deadline is fast approaching. We've extended it to the 30th of June 2021. So if you just go to the Warwick website, you'll be able to find out more information, and also on the BTS website. Next slide. As many of you are aware, we have been running a series of collaboration CPD courses between the BTS and the University of Warwick. We've held 3 of those to date. We have 1 more coming up on finite element analysis in tunnelling between the 13th and 15th of July. For further details and the booking link, please see the BTS website. Next slide. The next part then is a reminder that we do have a post-lecture social tonight, so please join us on Zoom. I know it's not quite the same as meeting in person, but it's great to see lots of lovely faces. So please follow the link on here. Look forward to talking to you tonight. And I think Divik will be opening that just a little bit earlier tonight. So that probably will be open from 7, is that right? These are a couple of reminders about upcoming talks that we've got. So the next one is on Thursday, the 10th of July on Thames Tideway Tunnel. Next slide. So the next BTS Young Members Lunch and Learn is on Thursday, the 19th of August on the Warsaw Metro Line 2 extension. Next slide. And there is also a BTSYM evening lecture on the design of gaskets for segmentally lined tunnels with Mike King on Thursday, the 9th of September. Just a reminder that the BTS conference will be taking place from September the 30th to October the 1st. And we are still very hopeful for this taking place. So please come and find out more and join us at the event. Next slide. Hopefully you've managed to all find out about our songs, but if not, please follow the link on the slide so that you can listen to them and find out more. Just a bit of a reminder again about the progress updates with the BTS 50th anniversary book. We are still going through the vast number of stories that we've got from you all, and progress is definitely being made. We can keep going. We are incredibly thankful to all our sponsors to date, but we do still have a little bit of space for some more logos on the back cover. So if anyone is still interested in supporting us, we have had a phenomenal amount of interest and stories that have been put forward, and we're really keen to be able to share all of them with you. Next slide. And then just a reminder to find out everything about the BTS if you either follow the QR code, and these are all of some of the rest of our links. So thank you and good night.